Hello, I'm Ryan Black, and I'm going to take you through some basics of spectral processors. Now, if you've watched the introduction video, you'll remember that there are three primary processor types. Dynamic processors, which affect the amplitude of a signal, spectral processors, which will affect the frequency of that signal, and finally temporal processors, which will affect the time of that signal. Generally, these are delays and reverbs. In this walkthrough, we're going to check out spectral processors. Boom. So this second category, the spectral processors, come in two types, sort of three, which I'll talk about in a second. You have EQs or equalizers, and these include graphic EQs, which you can see on the bottom here. Often you'll see these in live sound settings, and they're particularly effective for eliminating specific resonant frequencies of a system or a room very quickly. So for live sound engineers, these tools are vital to having an effective, clear, no feedback mix. And then on the right here, you'll see a parametric, and sometimes you'll see the term semi-parametric, depending on how many parameters are available. But a parametric EQ is often what those folks who are more in recording studios and used to DAWs utilize. And they are also commonly found on individual channels in most analog consoles. So these are two different types of equalizers. Now there is also a third little category in there, which is a filter. And we're going to talk about that as well. And filters are a more crude tool that essentially cuts a certain range of frequencies out. In many DAWs, filters are found in parametric EQs. Before we get into the specifics of the processor, of the spectral processors, let's talk about what is the frequency spectrum, just to make sure we have an understanding of the broad concept here. Generally, as a musician, we'll talk about frequencies in terms of octaves, and octaves are a doubling of a specific frequency. So if we go from 250 hertz up to 500 hertz, we have an octave. Ba, bum. If we go 500 up to 1000, we also have an octave. Ba, bum. 1000 to 2000, 2000 to 4000, 4000 to 8000. In our brains, in Western musicians' heads, these intervals are the same. They are each an octave. But if we actually look at the frequency spectrum, the difference between 2000 and 4000 hertz is 2000 hertz, whereas the difference between 250 and 500 hertz is only 250 hertz. So there's clearly not a direct relationship between frequencies and our tonal pitch system. Frequency is measured, well, linearly, and the way our hearing mechanism works in our instruments is an exponential system. And so these ideas, which are directly connected to physics and the length of strings and what happens when you divide different ratios of strings, are incorporated into how the technical and the aesthetic come together for audio engineers in the frequency spectrum. But understanding of frequency and how it relates to pitch and octaves is essential to being able to very quickly and effectively utilize an EQ. Another side note is the frequency spectrum that engineers deal with is significantly larger than the pitch spectrum that musicians think in terms of. So musicians might think through 2 to 3 octaves. Piano player would get more extreme than that, but a horn player or a singer is probably not thinking through 5 different octaves, like let me choose that pitch and that pitch. Audio engineers, we are responsible for more than 10 octaves on every single instrument. So it's not just about pitch, it's actually about all of the other things that go into creating sound, and timbre is the key term that I might use in describing sort of an EQ. The human hearing range is about 20 to 20,000 hertz, which, as I mentioned, is about 10 octaves. All right, so let's jump first to that third-ish category I mentioned, which is called filters. And these are circuits or algorithms in a computer that only allow specific frequency bands to pass through them. They filter out what you don't want. That can mean a low pass filter, which allows low frequencies to pass through, or a high pass filter, which is very common on pretty much every audio track, besides those that have the extreme low frequency range. Here, and you can see a little definition of equalizers or amplifiers that provide both positive and negative gain to specific bands or ranges of frequency. Now, if we look at our types of filters here, we have high pass, low pass, band pass, and band reject filters, specifically called notch filters, which are found on that graphic EQ that I showed you, right? This little fader applies to a very specific, in this case, 1/3 of an octave range of frequencies. And I can boost that on most graphic EQs. I can boost that by 12 decibels or cut it by 12 decibels. I would argue that what we're seeing here on this graphic EQ is not anything I would ever do in a professional setting where I'm kicking up 20 hertz down here and probably 16.5 or 18,000 hertz up here. Like, this is just sizzle noise in the signal. So this is not a great example of how to use a graphic EQ, but a good example of how they look. Those are specific band reject filters. Let's take a quick look at some of these. Here you have a high pass filter, which is allowing high frequencies to pass through. Sometimes you'll also hear the term low cut because we're cutting out the low frequencies. This is very common on most small, even analog consoles, but definitely something that can get overlooked in a DAW setting. You got to get rid of this sub-low frequency crap in signals. Just automatically assume you need a high pass filter unless you definitely don't, right? That's the way I think about it. High pass everything at like at least 80 hertz, maybe 60, maybe 100, maybe 110, but high pass everything. The exceptions being kick drums, sometimes bass, not all the time for me at least, and then sometimes keyboards, synth parts that actually are playing a bass role. You also have a low pass filter, which rejects the highest frequencies. This can be particularly useful if there's noise in a signal, sort of like a hissy thing that you don't need from a keyboard or something along those lines. I also use these pretty often on digital reverbs to sort of get rid of some of the higher artifacts of a room sound. And then you have a band pass filter, which allows it's essentially a low pass and a high pass combined, and allows a mid-range of frequencies, however you define that, to pass through. And that fourth category, the band reject, is what we see on those graphic EQs, which cuts out specific frequencies. Often these would be things like feedback frequencies or points in the system that resonate. So different speakers will resonate at different frequencies with specific microphones that will cause feedback that might be different from room to room or system to system. And being able to figure that out and adjust for that quickly is a key part of a live sound engineer's job, in my opinion. Like, if you can't do that, I don't know, you can't do the job. Here we have, sorry, a little cut off on the top there. Here we have a fully parametric EQ that includes a high pass and a low pass filter section. This is the Pro Tools EQ, the standard EQ. And what you can see is each frequency correlates in color. And this is, sorry, I should mention, this is a parametric EQ. And that frequency can be boosted or attenuated, this yellow one, for example. And the frequency can be modified, and the bandwidth, which is how wide or narrow that frequency is, can also be modified. In analog equipment, there's, I would argue, a lot more, like, you need to know your gear and really listen, because sometimes the way that circuitry works is pretty different from one processor to another. And now that we've started emulating a lot of that in the digital domain, it's really important to figure out if an EQ has undershoot, or if it bumps up, if it's a high pass filter or something, if it actually modifies the turnover frequency. And there's lots of little artifacts that analog EQs have that some of these early digital ones don't. And so they function differently and they sound different. You'll also see at the top end here, we have a shelving EQ, which is indicated by this little sideways Y diagram. And this increases all the high frequencies for the rest of the frequency spectrum. And you can also apply that on the low end if you wanted. In this case, this lowest band is not being used in that way. It's not even being used. You can see it has, that specific low band has been bypassed. So this specific EQ here has 7 bands, 2 of which are a high pass and a low pass, and then 5 of which are fully parametric. And fully parametric means they have frequency, bandwidth, and gain control. That is an overview of EQ and processors. And once again, just so it's on your radar, this is a graphic EQ, and the one that we were just looking at is a parametric EQ. And those two terms are key. And the parametric EQ also has a filter section, which allows us a high pass and a low pass. And these processors affect the frequency range. Excuse me. So I hope that makes sense. Those are spectral processors, and we'll do one more for temporal processors, and this will cover 95% of everything you'll use in practical audio recording or live sound or post-production. Thanks. See you next time.